we'll be talking about Ramsey meet Tautology, about theory change. Also, if you want to join us for the final conference of the year organized by Carnap, no, that's not good. Which is going to be the weekend of the first week of April. Please go to the website. You can check the program, and also we would appreciate if you want to register in advance, just to have a head count to know how many people will come to the conference. All right. Now it's my great pleasure to introduce someone who needs no introduction, really. Samir Okasha, who is Professor of Philosophy of Science at the University of Bristol. Samir worked in the philosophy of biology, extremely well known, was a leading philosopher of biology of this generation, maybe the leading philosopher of biology of this generation, and philosophy of science, general philosophy of science. He has published many books, often connected to some very large grants. I will mention only some of the book. The first one that he published was Evolution and the Levels of Selection, which won the 2009 Lakatos Prize. In 2018, he published Agents and Goals of Evolution, and Goals in Evolution, which was the result of an ERC grant in Europe. And I will also mention his 2019 book, Philosophy of Biology, a very short introduction. He was also the editor of a book called Evolution and Rationality, which was the result of an HRC grant on the topic. So he works on many areas in philosophy of biology, started by working on levels of selection. He has worked on the connection between game theory and biology, about the role of agency. In philosophy of science, his work is extremely diverse and touches a lot of different topics. His CV is really long, so I won't go through the details. He's published in all the important journals in the field, and also regularly in scientific journals too. And today we are very honored that he came to the last lecture of the year in the annual lecture series. And so anyway, Samir is going to be talking to us about the philosophy of fitness revisited. Samir, the floor is yours.
Great, thank you very much, Edward. Thank you all for coming. It's a great pleasure and honor to be here. I was just working out, I think it was almost exactly 20 years ago to the month that I last spoke in Pittsburgh, which makes me feel old. So the title of my talk is The Philosophy of Fitness Revisited, and the themes are as follows. The fitness concept in evolutionary biology, the opposition or disjunction, if you like, between philosophical and biological discussions of this topic. My sense that much of the philosophical literature on this concept is problematic in different ways. I'll try and expand on. What I propose as a new way forward, which will draw on two ideas that will be well known to, I think, everybody here from the general philosophy of science, which I'm going to try to put to use to understand this troublesome or apparently troublesome concept in evolutionary theory. And the first of those is the idea of a theoretical concept. I'm going to be proposing that the right way to make sense of what's going on here is to think of this concept and the term fitness as a theoretical term expressing a theoretical concept, and then to employ the so-called Ramsey, Carnap, Lewis approach to unpacking its meaning. Familiar to many people, I think. And the second general philosophical idea I want to use is the so-called model-first view of science, the idea that the typical scientific theory should be thought of as a collection of models, and not as an axiomatic system or as a set of general laws of nature or something like that. Again, a familiar opposition in the philosophy of science. So you'll know what I'm alluding to, I think, with these two ideas. So my project then is to try and apply these two ideas to the fitness concept in evolutionary biology. But I'm going to start by saying some things, some of which may sound a bit negative about the discussion of fitness. So the philosophy of fitness was a disparaging name that people gave to the philosophy of biology as a whole, this nascent new subdiscipline in the 1960s and 70s, as it was sort of crystallizing, perhaps I should say reinventing itself. I mean, there had been a philosophy of biology of sorts in the days of logical empiricism, but in its modern sort of incarnation, it came into existence in the 60s and 70s. A number of people who didn't really believe that there was room for such a project coined this disparaging label by way of getting at the question, why do they go on so much about fitness? Why do they talk so much about this thing? What's the big deal? And now, from my point of view, this question, in fact, this is the point, because the real question is not why people said so much about fitness, but why they discussed it at all, in fact. I mean, why think that this concept is amenable to or in need of philosophical analysis in the first place? I mean, not every scientific concept is. I mean, there are many scientific concepts that are important and interesting and we need to know about if you want to know that bit of science, but they're not unclear, or at least not in any way that a bit of philosophical analysis could ameliorate. And so for me, there's always been a bit of a puzzle about why this topic came to seem like fair game for philosophy at all. It's not obvious, the answer. I, in fact, think it is fair game for philosophy, but not in the way that other people do. In any case, despite that disparaging label, philosophical work on fitness burgeoned, and it's still ongoing, but it, to my mind, is a problematic literature, partly because it's not really clear what the project actually is in some of the discussions. And secondly, it's insufficiently integrated with the biology itself, tends to be based on overly simple models, not always a bad thing, in some ways. Good methodology, of course, to start with the simplest case. However, unfortunately, it also suffers from certain technical shortcomings. So I don't think of this body of philosophical literature as 100% reliable, I should say. And now in parallel, while all of that philosophical work analyzing the concept of fitness was going on, there's been extensive discussion in theoretical biology that began, I suppose, in the late 70s, but became bigger and more important in the 90s, about what the correct understanding of this fitness concept really is, and about what the correct mathematical fitness measure is under various different model assumptions in formal evolutionary models. And of course, this raises the question, not often treated exactly in that literature, what correct really means here, which is an important and interesting question. And in short, there are some pretty subtle conceptual issues here, but largely not ones that are discussed in the philosophy of biology. So to set the stage, I think it's useful to go back and think about what the origins of this fitness talk, or this word, is. And it lies, of course, in Darwin's frequent reference in The Origin of Species to the fit of organisms and their traits to the conditions of life or the environment, as we would say today. The fact that there's this striking concordance between the traits that organisms often exhibit and the very things that they would need to survive and flourish and reproduce in the environmental conditions that they find themselves in. Darwin, of course, wanted to explain how that fit came about. Only later, following Spencer's recommendation, did Darwin coin the expression "the survival of the fittest" as a sort of pithy shorthand to explain his process of descent with modification or natural selection. But in the mathematization of evolutionary theory that began in the 1920s, or the late 1910s, really, in the 1920s, fitness came to acquire a more specialized meaning. And indeed, something called a quantity called genotype fitness was a parameter of the early population genetic models that authors constructed by way of trying to formalize Darwin's own insights. Now, note well that you see, fit for Darwin, or fitness, was part of the explanandum of his theory. It was the observed phenomenon that things exhibited fit to the environment. That was something to be explained. And his explanation was the theory of evolution by natural selection. But fitness in the work of the population geneticists and in the 1920s and 30s, and still today in the evolutionary theory that they bequeathed or evolved from their work, fitness has become part of the explanans, in that the process that gives rise to well-adapted organisms is natural selection, and fitness is a theoretical term used in theories or models of that process. That's the sort of standard meaning of the term today. So the key point here is to make a distinction between the process of natural selection, of evolution by natural selection, and the things that that process gives rise to, the products, including the phenomenon of adaptation to the environment that we can observe in living organisms today, the thing that Darwin called their fit to the environment. And part of the subtlety and difficulty of this concept, I think, is that it appears on both the explanans and the explanandum side of evolutionary theory. And that, I mean, today it primarily belongs on the explanand side, but not entirely, as we'll see in a moment. And I think this is the first reason why there's more to this concept than meets the eye. Paper by Ulrich Kroes in 2022 makes a distinction between what he calls fittedness, and what Darwin meant, and fitness. Not vocabulary I'm going to use, because I prefer the orthodox term adaptedness to refer to what he calls fittedness. But I think he's quite right to notice that etymologically the word fitness can be employed to characterize both explanans and explanandum. Moving forward, then, fitness is, of course, a central concept in evolutionary biology today. And in some contexts, in the simplest ones, is entirely unproblematic, what it means and how it's measured. However, unclarities and ambiguities and disagreements surrounding this concept do arise and really exist out there in the literature, philosophical and scientific. But one point to make is that it's not really obvious why or how this could be. And I think that there are such unclarities and disagreements, both implicit and overt, is itself something we need to reflect on. Say, well, how could that be? But as you see, the science itself is not really in dispute most of the time. And indeed, modern evolutionary theory is a highly sophisticated branch of science, which achieved a great integration between theory and empirical data, particularly in the light of molecular biology. So the first thing I want to do, one thing I want to do is suggest an answer to this question of how it is that the science can be not in dispute, really, and yet one of the key theoretical terms can appear to be lacking a precise definition and the locus of disagreements between some of the practitioners of the science and the philosophical commentators on it. That's one thing I want to address. And I'll elaborate a bit more on that by posing what, to my mind, is a sort of prima facie puzzle or paradox in the loose sense of the word. So as we've seen, fitness is a key part of Darwinian evolution. The natural selection is meant to require that there be differences in fitness between different types of organism, or different type can refer to the genotype or phenotypic trait that an organism has. And natural selection is, of course, a very well understood process, both theoretically and empirically, extensively studied and modeled. And moreover, at root seems a very simple matter. And this is something that's said again and again, both in the science and in the philosophy, that, really, stripped of all of the fancy stuff, evolution by natural selection is a very simple idea. It's sort of so simple, it's amazing that no one thought of it before Darwin. This is something that Daniel Dennett says again and again. I think he's right. And many people say, look, you can actually boil the theory of evolution by natural selection down to something you can express in pretty much a simple single sentence, and everything else is just the logical consequences of that, which are not obvious, incidentally. That's why there's some science to be done. But at root, it's a very simple thing. But if that's the case, why then, or how then, could fitness be a contested concept? That's the puzzle. And this idea that one can boil evolution by natural selection down to something really quite pithy and succinct is found in a number of scientific and philosophical papers. So in a famous characterization of evolution by natural selection, which Lewontin in 1970 gave what he called his his tripartite analysis of the conditions needed for a population to evolve by natural selection. And he said, look, it's very simple. All you need is for there to be variation, so the organisms aren't all alike. But that variation to correlate with differences in this thing, fitness. And moreover, for the variation or the trait that exhibits variation to be heritable, passed down, greater than average tendency to offspring. And if you've got that, then over time, the population's composition would change as the fitter variants supplant the less fit. And Lewontin argues quite plausibly, this is the logical essence of Darwin's theory, and everything else follows from it. Although these authors didn't make any reference to each other's work, George Price, in the famous formalism that came to be called the Price equation, the covariance formulation of evolution by natural selection, essentially expressed in simple mathematical form what exactly Lewontin was saying by producing an equation which described for us the change in the mean value in a population of some trait. That's the trait Z, and Z bar then on the left-hand side is its mean value, and delta Z bar, its change over a population. So this could be the change in the frequency of some particular allele at a genetic locus in a population from one generation to another, or it could be the change in the average height in the population, depending on how we define Z. And then Price pointed out that in the circumstance, at least where the trait is perfectly heritable, where offspring inherit the value of Z from their parents, then this change is simply given by the covariance across the population of an individual's value of this trait Z with their quantity that he called their fitness, WI, all normalized by the average fitness in the population. So this just simply gives mathematical expression to the neo-Darwinian idea that genes associated with higher fitness will become more common over time, those associated with lower fitness less common. And the thing to notice is that in this equation, which many people sort of think of as encapsulating the essence of Darwinian evolution in mathematical form, that the term fitness WI has a simple definition. There's no latitude about what it might mean. It must just refer to number of offspring an organism contributes to the next generation. If it has any other meaning other than up to multiplication by positive constant, then the equation simply won't be true. There's no hint of any conceptual difficulty here. And yet, we find many expressions in the biological literature of the thought that this fitness business is pretty tricky. So the well-known biologist Stephen Sarnes wrote in 1975 that fitness is something everyone understands but no one can define. Richard Dawkins wrote in his 1982 book, The Extended Phenotype, a chapter entitled An Agony in 5 Fits, that he described as the most horrible chapter of the book to have written, in which he recommended, in fact, that the concept, or the word at least, be abolished. It caused more confusion than anything else, in his opinion, in biology. So sort of faced with comments like this, one thing you might think, and this is what I thought when I came across these comments, is, go and see what the pioneers of modern evolutionary theory in its mathematical formulation at least meant by the term. So we look at that. One of these was the famous J.B.S. Haldane, and his flagship semi-popular book, The Causes of Evolution, published in 1932, indeed has a chapter called What is Fitness? Great. See what this pioneer of modern evolutionary theory meant by the term. But the oddity of the chapter is that in that chapter he does many interesting things, but he doesn't tell you the answer to that question, and moreover doesn't even address it. The word fitness doesn't occur once in the body of that chapter. It only occurs in the title. So you're sort of left saying, okay, well, what's going on here? Now, Haldane's sort of reticence on this point might stem from his belief that it was a tricky concept, because elsewhere Haldane's reported have said that fitness is a bugger. So a comment he made in verbal discussion or in print. So next I thought, well, I mean, maybe Haldane is not the man. Why not look at R.A. Fisher? I mean, if there's sort of one person to whom modern evolutionary theory owes more than anything, almost everyone will tell you it's R.A. Fisher, Genetical Theory of Evolution of Natural Selection, rather, in 1930. And in that book, Fisher gives what appears to be a very simple, straightforward definition of the fitness of a genotype. As in, population containing different genotypes subject to natural selection, where Fisher says it simply means the instantaneous rate of change in numbers of individuals of that genotype, or the so-called Malthusian parameter, 1 over ND NDT. That seems straightforward. Fisher says that measures the survival, the fitness of each genotype in a situation where there's natural selection. But this definition has caused controversy. And as recently as 2019, we found Warren Ewan's very eminent leading population geneticist, saying that this definition of Fisher was an unthinking aberration, and he couldn't possibly have meant it if he thought for more than a few seconds about it. It's very odd. You think, well, the master theoretician said something that was an unthinking aberration. I mean, basically what Ewans is getting at here is that in a sexual population, is what Fisher was talking about, then individuals with a certain genotype can be produced by recombination from parents who don't have that genotype. And so therefore the change in numbers of individuals with that genotype need not reflect entirely what one intuitively might call fitness, but will also reflect the rate at which individuals with that genotype are born. In any case, another place I looked for was in the work of the leading evolution theorist Brian Charlesworth, sort of stalwarts of British evolutionary theory over many, many decades. His landmark study of age-structured populations where one explicitly models the age of organisms rather than just assuming that everyone's born at the same time. And Charles comes to the conclusion there's actually no such thing as a genotype's fitness. That sounds a bit odd. You might have said, well, we thought natural selection meant that genotypes differ in their fitness. But here he's saying, well, there's no such thing. When you understand what he means by it, it's not really that puzzling. It's interesting, but it's not as paradoxical as it sounds. But you see why the concept seems to call for a little bit of elucidation. Another final comment about the problematic nature of this concept is the question of fitness maximization. What's the status of that concept, and what exactly do we mean when we talk about the maximization of fitness? Actually, it meant different things to different authors. For some authors, this is no more controversial than the idea of adaptation itself, that organisms have traits that equip them to survive in their environment. Because presumably what that means is, had they had different traits from some set, then they would have done less well. So the one they have actually must maximize their fitness. So for some authors, this is not a controversial notion, but it's in fact just a simple way of formalizing the pre-theoretic notion of adaptation, fit to the environment. However, other authors insist that any talk of fitness maximization is an unwarranted extrapolation from simple models, and that no such maximization principle is a general truth about evolving systems at all. Another point to note is that, I mean, you might say, well, can't we, sort of resolve this just by seeing how the word is used? Now, in some cases, sometimes in philosophy of science, that's a good starting point. I think it's rarely the end point. You usually do something a bit better than that. But seeing how scientific terms used is clearly the first port of call to understanding the concept it expresses. But we find no uniformity, in fact, in this regard. And indeed, moreover, we find a plethora of fitness-like concepts. Here are just a few I list from modern papers and books on the theory of evolution. Notion of genotype fitness, notion of malleal or genes marginal fitness, notion of individual fitness, a quantity called lifetime reproductive success of an individual organism, the intrinsic growth rate of a gene or a type, a quantity referred to as the reproductive value weighted number of offspring, of which more in a moment, a quantity called the invasion fitness of a type or strategy, a quantity called inclusive fitness, a quantity called ecological fitness. So on the face of it, if you just take this at face value, taking stuff at face value is not good enough. You've got to go beyond that and understand what's going on. But just if one just looked at the way the words used, you would come away, I think, quite confused. In the term is in fact polysemic, also ambiguous, invalid. And one, I think, task is to try and explain that, why that is and how that came to be, compatibly with the fact that the science isn't really in dispute. So then, this is the background to this project I'm currently engaged in, which sort of revisits the fitness concept. And the aim is partly to integrate better the philosophical and biological discussions. I mean, this unfortunate situation of parallel literatures on the topic, in fact, it's not uncommon in philosophy of science to find that, but it's never good. And this is a particularly extreme example of it. The participants in these two parallel streams don't even know of each other's existence most of the time. I'm going to isolate what I think the real issues are, or some of them. Explain how the ambiguity or apparent ambiguity in regard to what fitness is arose and persists. Explain how it is that the term can be polysemic, and then resolve or shed light on at least a number of extant controversies about fitness in literature. This is the topic of a forthcoming book that will hopefully be around next year that I'm writing, co-authoring with philosopher called Ben Dance. Okay, so my starting idea then is simply that fitness is a theoretical concept. And I think this is right. I mean, that basically means that it's defined by its role in the theory. It's not simply some, metric attribute of an organism you can, like its height or its weight or something. It's not like that. So such concepts are defined by their theoretical role, I take it, and it's typically expressed by new terms, or at least maybe not, wholly invented terms in some cases, or repurposed terms from the vernacular English or whatever language is in question. And of course, to understand such terms, one needs to learn the relevant theory. I mean, sometimes you can sort of say something about what the term means. So if a kid asks you, what energy is, then you can sort of give them a rough and ready story. But of course, to really understand the concept, you've got to learn a bit of the relevant science. And so it is with fitness, I think. It's a crude definition of what we're talking about, but to really get what's going on, you've got to see the role the concept plays in the theory. Now, of course, talk of theoretical role sounds nice, but sometimes when I've presented this idea to scientists, they've said, yeah, but what does that really mean? Is that just a metaphor? That's indeed a good question. But of course, Carnap and Lewis famously made this notion precise, building on the early article of Frank Ramsey, Theories, 1992. Probably be familiar to many philosophers of science, and achieves its canonical formulation in Lewis's 1970 paper, How to Define Theoretical Terms, where Lewis insists, against the philosophical current of the time, that theoretical terms can be defined in science explicitly. And the starting point for the Carnap-Lewis project, I think, was this belief or realization that some scientific theories, at least, seem to do two things at once, and you might wonder how that's possible. I mean, on the one hand, they advance new empirical claims. They say something about what the world is like. In good case, that's hopefully will be true, something we can confirm, get some evidence that bears on it. So first job of a theory, obviously, is to say something about the world. But then some theories do that by means of new theoretical vocabulary that wasn't in use before. And so therefore, presumably, its meaning is implicitly fixed by the theory itself. So it seems that the one and the same thing, one and the same body of theory, is both serving to say something about the world and to implicitly define new terms used in that theory with meaning. And they sort of rightly, I think, said, well, how can you do that? How is that possible? And ordinarily, if you make a claim about the world, if you said the bumblebee population in Pittsburgh is declining or something, then you use words that have a pre-existing meaning. That's how you're able to make a determinate claim. So how is it possible to make empirical claims while simultaneously defining new terms? That was their problematic. And the answer that they proposed is that in principle, any scientific theory, when formalized in a certain way, can be split into two components, the conjunction of which is equivalent to the theory itself, and one component of which does each of those jobs. And that explains how it's possible for theories to do this sort of dual thing. And to illustrate the very simplest case, suppose a scientific theory contains one new theoretical term, T. So then the first component of the theory says, look, there exists something in the world that satisfies a certain description. And the second component says, if there exists something in the world that satisfies that description, then that thing is T. So the first component is, of course, the Ramsey sentence of the theory. The second component, sometimes known as the Carnap sentence, which in conjunction is logically equivalent to the theory itself. And this then allows us to explicitly define the theoretical term T as a unique entity in the world, if there is one, that satisfies the description, the role description in question. So to illustrate this with a biological example, I mean, the canonical illustrations of this are usually from physics, but in principle, it applies anywhere. Consider the field of classical genetics. This is before molecular genetics, before DNA, when a gene was simply a hypothesized particle designed to explain what one saw in breeding experiments, or experimental cross fruit flies, typically was. Just then a body of theory that I referred to from about 1950, 1940s and 50s. And I think the role description of the term gene in that body of theory was something like this. Genes are transmitted from parents to gametes. They obey the law of segregation, they come in variant forms, they determine an aspect of phenotype, they exhibit different degrees of linkage with each other, refers to the probability of co-inheritance. And then a classical gene is just whatever entity out there in the world plays that role. A unique realization is not a given. It's an open question that historians of science have grappled with about whether there really are such things as classical genes, and whether that really is realized by something describable in the language of modern molecular genetics. But in short, that's how one would isolate the theoretical role of the term, by means of something like that. How do we apply this to evolutionary theory? Well, here there's a problem, of course, because you see, the Carnap-Lewis approach, well, I mean, is presupposing that a scientific theory can be expressed as a finite set of sentences in first-order logic. So-called received view of what a scientific theory is. As many of us know, then real scientific theories don't look much like that. Can you force them into that format? Yeah, probably, but not much point. And it's even if you did, well, it's not really obvious how you would do that anyway. So this model, of course, is a poor fit with real science. And beginning in the 1960s, philosophers of science have long been attracted to the so-called model-centric view, which places the notion of model at center stage in understanding the scientific enterprise. So I'm sure telling you things that are bread and butter to many people here. I should mention here an interesting, though largely forgotten project by an author called Mary Williams, who tried to apply something like the received view to evolutionary theory in a couple of papers in 1970, early 1970s, where she tries to actually explicitly axiomatize Darwinian theory, taking the term fitness as a primitive. And now, for a number of reasons, her project doesn't really work, I think. However, had it done, I mean, the Carnap-Lewis approach could have been applied exactly to what she was trying to do there. And it's somewhat ironic because she took her one of the morals of her own work to be that the term was a primitive that couldn't be defined. And yet, had her own maximization worked, then you could precisely have defined it via the Ramsey settings technique. But anyway. So the second philosophical idea then that I want to propound is that we should think of evolutionary theory as a family of models. I don't think that it's particularly controversial. I mean, if you take out a book about evolutionary theory, then you find lots and lots of mathematical models of the evolutionary process in there. So it doesn't seem like too much of a stretch. And indeed, when you explain this to evolutionary biologists, then they sort of say, well, yeah, that's obvious, isn't it? But of course, I mean, it's not the claim has more content than just saying they make people in math, science, area of science make models. The claim is that this is the source of the generality lies in those models and not in some set of generalizations that they will instantiate. So it's not meant to be a sort of trivial sociological observation. But it contrasts, of course, with the received view, and I think with the attempt to boil evolutionary theory down to a few fundamental principles from which all else follows, of which I gave you the examples of Leontin and Price, and many others, and Dawkins associated with that project too. So I think it's not a triviality exactly, but I think captures the structure of the science that we call evolutionary theory far better than that received view story. But you see, if that's right, then it becomes a little unclear how you apply the Lewis Carnap Ramsey approach. Because the letter of that approach requires that the theory be a set of sentences in philosophical language. So, but what I want to suggest, and I think it's an obvious idea, and I think other people, in fact, have probably done this too, is to say, look, we can preserve the idea of a theoretical concept being defined by its theoretical role, and the crucial distinction between the role and the realizer, the thing, the quantity in this case, would be that realizes or plays that role under certain assumptions, while dropping the idea of a theory as an axiomatic system, as a set of sentences, expressible in a logical language, but thinking of it as a family of models. So we employ then not the letter but the spirit of the Carnap-Lewis approach. That's what I'm trying to do. Embrace the idea of theoretical concept defined by its theoretical role, drop the bit about what a scientific theory looks like. Okay, but how do we do that? Well, okay, if you accept that sounds about right. How do we implement? Well, the first task then, in application to the science I'm interested in here, is to identify the theoretical role of fitness in the fitness concept. Not by looking at actual usage, although that's a start, because it's not very uniform, nor by hunting for some definition, just straight off the bat, but rather asking what job the concept is meant to do. And I think, in fact, this methodology is implicit in some discussions of fitness, particularly in the biology literature, where people make arguments of the form, look, this is the right mathematical fitness measure in certain circumstances because it has certain properties. There are such arguments out there. And what I'm saying is, we can capture the logic of such arguments just by saying, state up front what those properties are, and then define fitness as the thing that has it. And here I think we missed a bit of a trick in the philosophy of science, in philosophy of biology on this topic, in that many so-called definitions of fitness are really something else, I think. And one thing that I think philosophy could usefully have done is attend more carefully to the logical form that a definition of fitness should really have. As you see, the term definition is used rather loosely in many bits of science, including this one. So when people say, look, here's the definition of fitness, you shouldn't really take it as given that means definition in our strict philosophical sense. Here I want to briefly intersperse and go back a bit, in fact, to something that was the origin of much of the philosophical interest in fitness. And I think it's a salutary lesson in why it's crucial to attend to the role that the fitness concept is meant to play in the science. So in the 1960s and 70s, Popper famously put forward something that came to be called the tautology objection, in which he argued that Survival of the fittest, this sort of Darwinian slogan, is an empty tautology, as the fittest is just defined as the ones who survive. And that the core evolutionary principle he maintained, he said, is a logical truism, as he put it, and he went further and said that therefore the whole theory of evolution is a metaphysical research program. In the, of course, writing in the days when to call something metaphysical was not to praise it. Now, Popper partly recants this rather exaggerated claim. However, the tautology objection sort of rumbled on and is still sometimes raised today. A better version of it takes account of the fact that what we really care about in evolution is not just survival, but reproduction too. And is sometimes formulated as follows. People say, look, if fitness, the fitness of something, of an individual organism, say, is defined as its actual number of offspring, its lifetime reproductive success, then tautology results. It's the claim that the fittest types will predominate in the population becomes true by definition. And again, the charge is similar to what Popper said, that there's an apparent circularity right at the heart of the theory of evolution. But then how can the theory have the explanatory power that we always think it does have? This alleged puzzle gave rise to a lot of discussion. And I think the canonical version of it is a much cited paper discussed by Mills and Beattie that spawned an enormous, vast philosophical literature that continues to this day in one form or another, and became associated with something called the propensity interpretation of fitness. But what I want to do, I mean, there's much of value in this paper, but I think at the critical juncture, they actually equivocate on what they think the job of the fitness concept is. So this is a lesson in why it's really critical to attend to that question. Look at how they argue. The first thing they say is this: A and B here refer to different heritable types of organism in a population, genes, if you like, or traits. They say clearly we cannot say that the difference in fitness of A and B explains the difference in actual average offspring contribution between A and B, when fitness is defined in terms of actual reproductive success. Now that indeed seems clear because it's an instance of the point that nothing can explain itself. So if what it is for A and B to differ in fitness is for the actual average offspring contribution between A and B to be different, then clearly that A and B differ in fitness cannot explain that fact. That I think can hardly be disputed. However, Mills and Beattie then go on to say, then there's a big problem, because they say, yet evolutionary biologists seem to think that evolutionary changes can be explained by invoking the relative fitnesses of the types concerned. So notice that suddenly they've changed from talking about explaining differences in actual average offspring contribution to explaining evolutionary changes. Not the same thing by any means. And that a certain definition of fitness precludes fitness differences being able to explain the first thing, because they just are that thing, in no way precludes them from explaining the second thing. Now, I'm not just picking at some words here. This is actually the logical crux of their argument. And I think it's the crucial point to note is that, you see, very often in biology, we do define fitness in terms of actual reproductive success. But it still isn't trivially true that differences in fitness so defined explain observed evolutionary changes, that's to say, changing proportions of the types from one generation to another. It could have been mutation. Right. So the second thing is right. The first thing is right too. But these are very, very different claims. And that a certain definition of fitness is incompatible with fitness doing the first thing doesn't show that it's incompatible with it doing the second thing. And indeed, the first thing is not a genuine role of fitness at all, whereas the second is. Now, three standard reactions to this tautology thing in Mills and Beattie version. One is to say, look, survival of the fittest, just a handy slogan. Don't take it so literally. Another is to say, yeah, it is tautological in a sense, the principle of natural selection, but somehow or other that doesn't matter. It doesn't impugn the explanatory power of theory. And the third is to say, well, maybe if fitness was suitably defined, the tautology would be eliminated. And this indeed is Mills and Beattie's own route, and gave rise to a large body of discussion where people talked about something they called the propensity interpretation of fitness. Sort of modeled on the propensity interpretation of probability. And a number of things to say about this. I mean, the first thing is that the case for thinking that you should think of fitness as a propensity hasn't been made out, precisely because of this equivocation here. Now, it's certainly true that in some evolutionary models, when one is explicitly modeling stochastic factors of one sort or another, one talks about the probability that an organism of a certain type will be various different numbers of offspring. Those probabilities, of course, are objective. And so it might be possible to think of those as propensities if one's persuaded by the propensity interpretation of probability more generally. So it's not that this idea is completely wrong. However, the rationale for this has not been made out. And that even if fitness is defined in terms of actual reproduction, no threat of triviality arises. And fitness, moreover, is sometimes, not always, but sometimes precisely defined that way. And this point, incidentally, has been obscured by a sort of notational problems tripped up many philosophers of biology, which is that often in evolutionary models, one finds reference to something called the expected number of offspring of an individual of a certain genotype. And it's natural when people read that, think, oh, okay, then there must be probability distribution. We're talking about over numbers of possible offspring. So therefore, we'll think of that as having the propensity to be different offspring. But you see, very often, and indeed always in deterministic models of evolution, where this phrase expected number of offspring is used, then it's important to understand what the random variable is that we're taking the expectation of. And it's simply defined by the random experiment of picking an organism of the genotype at random. And so really, what we're doing is averaging over the actual reproductive success of members of that genotype. And now there's nothing very puzzling about what's going on. It's just an instance of the familiar statistical practice of taking the population mean, or true mean, of some attribute in a population to be the expected value of a particular random variable defined by picking an organism at random from that population, similar value of the traded hat, of the attributed hat. Statisticians will usually use the same letter, mu, for both of those things. And equating them is perfectly okay. It obscures the fact that we are actually precisely talking about actual reproductive success here in many, though not all, references to expected number of offspring. So anyway, that's that little interlude aside. And I hope it illustrates why it's critical to focus attention on what exactly the role of fitness is meant to be. I maintain that, in fact, there are 4 such roles. And that in simple cases, the same quantity plays all 4 roles, but in more complex cases, that's not true. And therein lies the sort of source of the polysemy or ambiguity in the term. The first is what I call measure of selective advantage. I'll expand on these in a moment. Second is a predictor of the evolutionary outcome. Third is a determiner of the evolutionary dynamics. The fourth is a measure of adaptiveness. Now, 1 and 3 concern fitness in its role as explanand, as a term used in models of the process of evolution by natural selection. Whereas role 4, on the other hand, is a bit different, and this refers to fitness as used to characterize the products of that process, the well-adapted organisms that we see. Raise the question, well, which, if any, role is privileged? And there's a lot can be said about that, but I won't go into that for now, except to say that these enable you to answer somewhat different questions. So depending on what exactly the question is you want to answer, then one of these fitness roles will be the relevant one. So my basic idea then as follows is that in any explicit evolutionary model, one can ask whether a particular quantity, definable typically from the model parameters, does or does not play one of those four fitness roles. The answer may be yes, maybe no. Maybe easy to see, or maybe actually very difficult to ascertain. Quite non-trivial work. Moreover, the same quantity may realize more than one of those roles, and that will be the case in nice cases. But that need not be so. And moreover, in different models, and under different model assumptions, one and the same role can be realized by different quantities. I'll illustrate these points in a moment. And this at root is why the concept is subtler and trickier and meets the eye. I should compare this with other taxonomies of the fitness concept that have been given. Well, let's speed up. One is that to classify by the entity that bears this property of fitness, the object that has the property. The point here is that sometimes we're talking about the fitness of an individual, sometimes of a type, such as a genotype, thought of as a group of individuals, sometimes of an allele, a gene, sometimes of a whole population. This distinction, this important distinction crosscuts our taxonomy of fitness roles. A bit more about each role. Measure of selective advantage, perhaps the most fundamental fitness concept or fitness role as I see it. I mean, suppose you have a set of types in the population, and we say what properties must a fitness function, a numerical function, defined on those types have in order to be a fitness function? Well, intuitively, it should satisfy the following principles. The fitness of type A exceeds that of B, then selection favors A over B. And moreover, if the fitness of all the types is equal, no selection takes place. Variation in fitness being a necessary condition for evolution by natural selection. Might wonder about whether that should be an if and only if. It's a long story about that. Won't detain us for now. Now, is this a substantial constraint on what it is for a numerical function to be a fitness function or not? Well, yes, if we know what selection means, of course. But I say there is an independent definition of selection we can appeal to, which is differential reproduction that's not due to chance. Which is perhaps the most basic meaning of the term. Presumes that you know what reproduction means. In fact, that's always trivial. And some people have employed a stronger notion of selection, according to which the differential reproduction must be due to some intrinsic aspect of the intrinsic feature of the competing types, rather than merely requiring that it not be due to chance. So in fact, that means that role one bifurcates into two. And it then becomes a substantive question whether any particular quantity realizes role one or not. So the probability of surviving to reproductive age in some evolutionary models will realize role one. In others, it won't, if there are differences in so-called fecundity. That's the first fitness role, fitness as measure of selective advantage. Second role is that a fitness measure is meant to predict the evolutionary outcome. Now, the outcome may refer to the fixation of one type elimination of others, may refer to an equilibrium, possibly polymorphic, where there are many types, or something else, maybe a non-equilibrium condition, state. Intuitively, the idea is that fitness is meant to be such that the fitter types should prevail in evolutionary competition, other things being equal. But how to make this precise depends on context and whether we can make a deterministic prediction, for example, or only a probabilistic prediction of the outcome is one crucial thing. And what exactly ceteris paribus must be taken to mean here is another crucial thing. In any case, that's the second role. What you want of a numerical fitness measure is to be able to say, oh, this one has the highest value of it, therefore we predict it will evolve. But again, evolve, the meaning of that you got to pin down. The third role of fitness is as a determinant of the evolutionary dynamics. The point being that evolution is really all just about change in frequency of things, change in the frequency of the different types in a population from one time to another, the most fundamental meaning of evolution. And one job of a fitness function is to allow us to convert old frequencies into new. Indeed, much of the purpose of at least some forms of evolutionary analysis is to precisely write a recursion equation that tells us, that allows us to express the new frequency of a type in terms of its old frequency and some other stuff. And that other stuff is fitness. So PT is the old frequency of the type. PT plus 1 is the frequency at the next time step, which I mean the next generation here. Then the fitness function should determine that change, delta P, given the population state of T. So if you know the fitness of each type, you know the old frequency, you should be able to compute the new frequency. That's their job of fitness, is constrained by that role, by that job. I say, is this really different from R1? Definitely the measure of selective advantage, yes. I mean, one reason is that role 1 is about selection, role 3 about evolutionary change. Another is that role 1 is merely order. That any fitness function that satisfies role 1, any monotone transform of that will also do so, not so for role 3. And then the final role of fitness is as a measure of how well adapted things are. This corresponds to Darwin's notion of fit to the environment. Now you might say, is this really a true fitness role at all? And you might think, well, perhaps we can capture the phenomenon of adaptation by some sort of trait-specific performance metric. So I don't know, measure how hard, a crab's carapace is or something, how good it is at protecting it from things that hit it or something. And so therefore measure how well adapted crabs are by some metric that makes no overt reference to function. And the correlation of such a metric with fitness will then explain how it is that crabs come to seem so well adapted. But the measure of adaptedness itself, you might think, need not make any reference to fitness. Well, there's a lot of things to be said about that. However, for the moment, I'd just make the sociological observation that the idea that adaptation or apparent design, the explanandum of the Darwinian theory, one of the explananda of the Darwinian theory of evolution, is correctly characterized as fitness maximization, is very much alive in evolutionary biology today. So I think we should hesitate before discarding this as a fitness role. So here's then the simplest possible case where all four the roles coincide, in the sense a single quantity realizes all four roles. Simplest case means it will be too simple to write an explicit model of, because we deliberately abstract away from all of the things that make evolutionary analysis difficult and interesting. But we imagine a very large population of haploid asexual organisms. Haploid means that one copy of each chromosome just inherit asexually from their mother. There are no males. Imagine two types, A and B, with initial frequencies P1 minus P, or PQ. Generations are discrete and non-overlapping. Every organism is the same age in the population. They reproduce and they die. It's a bit like annual plants fit this model. Most other things don't. We assume that the types breed true with no mutation. We assume there's no age nor class structure. I'll explain what that means in a moment. We assume the environment is fixed, doesn't vary stochastically. And then we define Wi as the per capita number of offspring of type I, where I ranges over A and B. And we assume that this is a fixed constant, stays fixed over generations. That means that there is neither frequency nor density dependence of fitness. This population can grow without bound. And then it's straightforward to show that this quantity Wi realizes all four of our fitness roles. If A has more of it than B, selection favors A over B, where selection was independently defined. If they're equal and there's no selection, the type with the highest value of W, that quantity W, must fix eventually. If you want to work out the new frequency of type A from its old frequency, all you need to do is multiply its old frequency by its value of W divided by the average population value of W. That's the denominator of that second right-hand side term. And moreover, Wi is a natural measure of adaptiveness. Why do I say that? Well, because at evolutionary equilibrium, when there's no more evolution going on, all the bees are gone, all individuals present in the population will exhibit the type, the phenotype that maximizes the value of I. And moreover, the population mean of Wi is maximum with respect to all other possible population compositions. So in two senses, logically distinct senses, the evolution has maximized fitness. So the Darwinian idea that natural selection leads to adaptation is indeed vindicated here if we take Wi as a measure of adaptiveness. Okay, so that's the simplest case, where it's all simple. However, in more complicated cases, a single quantity definable from model parameters may not realize all fitness roles, and indeed doesn't. And therein lies the difficulty, the fitness concept. The sort of decision has to be made about what we kind of mean. This accounts for the ambiguity. One illustration of this is that if we take into account the phenomenon of class structure, in any real population, individuals belong to many different classes. So they differ in age, different sex, some sexual populations, differ in their size, of birth, for example, might differ in their quality, might differ in their energy reserves. For some classes, then an individual will remain in its class all its life. Others, it'll move through different classes, age and sex, illustrations of that. The class here, just to informal order, this just refers to any partition of the population. Now, one consequence of taking into account this is that number of offspring, counting number of offspring, is no longer a good measure of an individual's fitness. As you see, those offspring might be different, belong to different classes. So, for example, an organism might be able to leave 3 high-quality offspring or 4 lower-quality ones. And if you just count numbers, you're missing something. Some crucial thing relevant to how evolution happens, you will miss. They differ in their evolutionary value. What's the solution to this problem? Well, one solution, this goes all the way back to Fisher, you mentioned before, is that you don't just do a simple count, you do a weighted count of offspring, where you weight each offspring by the reproductive value of the class to which it belongs. I did a quantity called the reproductive value. How do you exactly define that? Long story, but roughly speaking, what we refer to is the probability that a randomly chosen organism at some arbitrary point in the future will descend from that class. And then we can compute fitness as follows, not the simple count of offspring, but the reproductive weighted, value weighted count. But then the crucial question arises, why? Who says? If someone says this is the right measure of fitness, why is that? And then what you have to ask then is which of the fitness roles does that quantity play? And that becomes a non-trivial question. You know the answer, but you see why matters become a bit subtle. Another scenario arises when one considers environmental stochasticity. So a very large, important class of evolutionary models try and deal with the fact that the environmental state, say the weather, for example, generation is not always the same. They vary stochastically. So in the simplest models of this process, things, one considers a set of possible environmental states, probability distribution over them, assumed independent across generations. And then a familiar result says, well, the best way of working out a genotype's fitness is to consider the geometric average, geometric mean over that random environment of the per capita number of offspring of an organism of that genotype. In a sense that can be made precise, the type with the higher value of that quantity will predominate in the long run. But this is often regarded as the measure of fitness in a stochastic environment. But it's crucial to realize that this realizes role 2, the predictor role, in the long run, but doesn't realize role 3. If you want to work out the generation by generation expected change, the geometric mean quantity is not the quantity you need that's going to do that. So this is a concrete illustration of how it is that a certain quantity, very useful if your job is trying to predict what will happen eventually, will not do the job of enabling you to compute, in this case, the expected composition in the next generation. Expected is when it's random, so you don't know what it will be. And over finite time periods, it's not quite clear what the right fitness measure is role 2 is. I think I'll skip this next bit on finite populations because it's, well, no, maybe I'll quickly say. See, many the sort of simplest evolutionary models, you always assume the population is very big or technically infinite. That has enormous, I mean, it's biologically realistic some of the time, and has enormous mathematical advantage. It means that stochastic factors are independent across organisms. They just average out. So then we can make a so-called deterministic model, according to which we can actually work out, or definitely, what the population will be like in the next generation, rather than just computing the probability over the possible ways it might be. But if you take into account finiteness of the population, then things are a bit different. Now, one measure proposed by a guy called Gillespie that's generated a lot of interest, oddly, among philosophers, considers both the mean of an individual's number of offspring, where that's now the number of offspring any individual of a given genotype needs is now random. So Gillespie says, well, consider the mean, consider the variance of that distribution, and then divide that variance by the number of individuals in the population. And we arrive at this measure, and then he says that's the right measure of fitness in this finite population circumstance. A lot of philosophers thought that there's something interesting here. And in a sense there is, but it's crucial to see that this is the right fitness measure only in one sense. This plays one of the roles, the predictor role in the long run, but again, not the first or sort of third role. And indeed, in a recent paper in the theoretical biology literature, we find Thomas Hansen insisting that this is not the right definition of fitness, and in fact is attacking a lot of philosophers who he says have naively believed this. It's a bit unfair because this Gillespie guy was a sort of huge authority in mathematical population genetics in the 70s, so you can sort of see why philosophers like Ramsey said, so, well, he must be right. But I mean, partly this is just because he wasn't using the word definition in the strict sense of the term, and also wasn't distinguishing between the different jobs that one wants the fitness concept to do. So this again stems from differences in role. Skip that bit. Yeah, age structure. I'll say something quickly about this. I realize I'm running on a bit here. I hope you're all riveted. I mean, the usual way one takes into account age structure in the evolutionary model is to consider survival and fecundity as functions of an organism's, not just of its genotype, but also its age. Right. So for each genotype, I, we write down its probability of surviving to age X, LIX, and the number of offspring it will have if it does survive, MIX, for each genotype X. And then we're trying to work out again which genotype will do best. You might think, well, maybe what we should do here is just sum over all values of X and see which genotype has the higher value. That product summed over all the values of X. And that would measure the total life expected number of offspring over its lifetime that the organism has. In some cases, that's indeed the right thing. Not always. This is another thing you can do as well, right, when you've got these two functions in place, in that you can consider hypothetically a population that's homogeneous for the genotype and look at the rate at which it grows. And that intrinsic rate of increase is a function of LIX and of LX and MX. But can't be written as an explicit function often. It can only be expressed as an implicit function. And that's a different quantity, not the lifetime reproductive success. That's the quantity R. So then immediately you can say there's two different things you might think of as fitness here. Which is right? Well, again, it depends on model assumptions and on what you want, what question you want to answer. And this is the source of Charlesworth's remark that it's not possible to attach a single number to each genotype that will measure its genotype fitness. What he means that will play a certain role that he takes to be the fitness role, and which must be a single number attaching to the genotype, rather not to an organism of the genotype of a specific age. And this then is the source of a very puzzling discussion that went on in life history theory in the 1990s. A branch of evolutionary biology addresses questions like, what age should an organism stop growing and start reproducing? Should you reproduce once in your lifetime, like a cactus, or often, like a perennial plants, for example? Why? And the standard technique for addressing this question that people used back then was to construct what they call optimality models. Just to model the different possible strategies, life history strategies an organism could follow. One of which might be, grow for 3 years and then reproduce and then die. Another which might be grow for a year, reproduce, grow a bit more, reproduce, grow a bit more, reproduce, and then die. And then to ask which of them is optimal, but by what criteria? 2 different metrics that modelers were using. One was this intrinsic rate of increase, R. The other was a quantity called R0. It's just the lifetime number reproductive output, expected lifetime reproductive output, sometimes called the basic reproductive number in demography. And these don't give you the same answer. So again, the question arises, well, which of these is right? And it turns out that the answer partly depends on what you mean by right, and partly depends on model assumptions. And this was pointed out in a seminal paper by these guys, Mylius and Diekman. There was an operating with an implicit answer to the question, what does right mean? And then showed that, well, if you mean that, which they sort of said implied that you should, then under some model assumptions, little r does the trick. Under some model assumptions, R0 does the trick. And so it's not just a matter of subjective preference, as some modelers in the earlier literature, indeed very sophisticated modelers, had intimated. And what they're doing in making this argument is invoking something called invasion fitness, which measures the growth rate of a mutant, a single copy of trait Y or gene Y in an environment where that's otherwise contains only organisms of type X. So the idea is you see what the growth rate of a rare mutant is growing in a resident population. And if it's bigger than the growth rate of the resident itself, then it can invade, and otherwise not. This is the basis of all evolutionary game theory, in fact. It's sometimes described as the master fitness concept. And many people say, one idea out there is, look, any plausible fitness definition has got to be sign equivalent with the invasion fitness, but the ordinary equivalent to the invasion fitness, if it's going to be a valid fitness measure. And in a sense, that's true. But you see, this is only, again, interested in role 2 and role 4 of the fitness roles, predicting the outcome and measuring adaptation. If you're interested in the step-by-step evolutionary dynamics, that's explicitly not being modeled in invasion analysis. And the whole point of it is to say, look, forget about that. Just look at equilibrium points. Look at where the population will end up. Don't worry about the sequence changes. So the fitness concept that they use, unsurprisingly, it doesn't allow you to compute the step-by-step changes. So although in a sense it's right to say this is the master fitness concept, as many authors now do, it's important to see it only plays some of those 4 roles. Inclusive fitness, this is a long story. Some people may have heard about this. So it's well known that altruistic organisms, that's ones who sort of help others at a cost to themselves, it's common in social species. Clearly, whatever they're doing, they're not maximizing their personal fitness, because if they were, they wouldn't do that thing. They wouldn't share food with others. They would consume it themselves. Or they would risk their life to warn their group of a predator. They would just climb the first tree themselves. And now Darwin puzzled over this phenomenon. But a key idea that came from the English biologist William Hamilton in the 1960s was that they are in fact maximizing something, but a quantity called inclusive fitness, which is a more complicated measure that takes into account not just number of offspring an organism leaves, but also the effect it has on its relatives' reproduction. This more complicated measure, Hamilton claimed, is the measure that's being maximized when you see altruistic organisms. Influential but controversial, it's led to an enormous storm in biology, one about whether this is a well-defined concept. Another question then to ask is what role it really plays. Hamilton's vocal modern followers insist that it plays role 4. This is the true beauty of the role. It serves to measure how well adapted organisms' social behavior is. However, that's a debatable claim because you see the most general models really only show something much different, which is that you can always define an inclusive fitness such that it will play role 3, allow you to express the evolutionary change over a single generation in terms of this quantity inclusive fitness. But it doesn't follow from that it plays role 4. So they're almost finished now. So you see, if the way I've been setting it up is right, then it follows that there are two and only two possible sorts of disagreements you can have about fitness. I mean, other than the third sort where something's just wrong, but two sort of cases where it's not simply that there's a mistake. And the first sort is that there's a disagreement about roles. Some people are implicitly perhaps prioritizing one fitness role, predicting the long-term outcome of evolution. Others are prioritizing a different role, being able to compute the next generation frequency from the current one, or measuring how well adapted organisms are, for example. And that's the source of the disagreement. Second one is very different. Second one is that both parties are thinking about the same role, but they're making, again, implicitly or explicitly, different model assumptions, and under those different model assumptions, a different quantity will realize that single role. And so the final chapter of my book, fortunately, which I'm not going to go through here, what I do is sort of run through a kind of 10 case studies of debates that one sees about fitness and tries to show how each of them is either of type 1 or of type 2. I mean, both could be in play at the same time, of course. And I say there's no other possibility unless one party has just sort of got it all wrong. Shouldn't discount either. So I mentioned one of those debates between little r and R0 as the optimality criterion, inclusive fitness or not. This notion of Fisherian fitness, is that a good measure of fitness or not? The business of weighting by reproductive value and why. One I haven't mentioned yet, and this is the question of whether we should mean by fitness the number of offspring you make counted at conception, or whether you should wait a bit and see how long they survive. Some people say, well, wait a minute, it's all very well producing lots of offspring, but if none of them survive very long, that's not very good. Okay, then how long should they have to survive? Do they have to become recruits, as ecologists say, into the whole population? So is it up to adulthood to survive? Up to the age when they can reproduce themselves? And why? Really interesting debate on that point. And again, it's the question, why is the critical one? Why is that the right measure? I mentioned this geometric mean fitness issue. Another question of whether the right measure of fitness is ultimately in a finite population, again, is the probability of fixation of the gene or not. Some people say, yeah, that's the true measure. Other people say, well, wait a minute, that could be in 1,000 generations. That doesn't answer the question we want. Invasion fitness is the master concept. So to conclude then, I think the fitness concept is indeed subtle. It's not just an ordinary property of an organism, just sort of unambiguously measured, because it's constrained by the theoretical role it's meant to play. And in fact, I say it plays multiple roles. And the critical is this role realizer distinction, and the attendant realization, or attendant fact that many things that are described as fitness definitions are really statements to the effect that a certain quantity realizes one of the fitness roles under a certain model assumption, which is not a definition in strict sense. I think the philosophical discussion is largely misplaced. I mean, could elaborate more on that if people want. I mean, partly because it's based on simple models where in fact the concept's entirely unproblematic. So bizarrely, people have sort of tried to problematize something that's not problematic and missed the real problems in the philosophy of biology discussion of this. And this, I think, explains this how there can be these genuine fitness disagreements, despite the science not being in dispute. And also explains, I think, another thing that's often said, which is that there's no single mathematical fitness measure that will work in every model. And again, you might say, well, why not? Surely there should be. And it explains also the plethora of fitness-like quantities that one can find out there from the sort of superficial glance of the science. Okay, so I say then a philosophy of fitness is indeed possible, but the real issues are somewhat different to the ones discussed in much of the philosophical literature, old and new, on this. And I think the positive moral is that philosophy of science really can help here. And I've tried to put to work two ideas that I think are sort of independently defensible in the philosophy of science. First is the scientific theory as a family of models idea. And the second is the idea of theoretical concepts being defined by the Ramsey, Carnap, Lewis technique. And I think those give you the framework for a better understanding of this troublesome concept. Thank you all for listening. I'm aware of how long I've been.
All right, please, if you have a question, raise your hand. Please go ahead.
Thanks. So at some point you had this function W of I, just take an example. I think it was in a very simple case.
Yeah.
And this was like it plays all the role.
Yeah.
But there seems to be naively, perhaps, much biology, there's a perfect question someone asked, which is why this function Y, or maybe W, sorry. Why is this particular value of W attached to this member of the species I? So I say, well, because say W is high. So then, well, because I is fit, then you're in the tautology. So is that a question not allowed to ask in biology?
No, good. That's excellent. That's exactly right. That, as I say, yeah, if we say, why is it that type A has a high value of W, type B a low value, then the explanation of that must not involve anything to do with fitness. And I think doesn't. Basically, will appeal to the fact that the environment's a certain way, that organisms with type I are a certain way. And taken together, the underlying causal model will be environment, genotype, arrow, W. And it's a mistake to think that there's some intermediate. Don't worry.
Want to draw something?
Yeah, I was going to. That there's an intermediate variable in the causal model, which is called an organism's fitness or something. And that's one of the things that Mills and Beattie are I think, getting wrong. So I think you're absolutely right. Thank you. But if someone, I am indeed taking it for granted, and I think it's right to do so, that the causal explanation of why it is that one type, say A, has a higher value of this function W than another type, say B, will not say anything about the fitness of type A and B. In the underlying causal model is simply genotype, environment, W. And now some people admittedly have talked as if the underlying causal model is sort of somewhat more complicated and involves some sort of other thing here called fitness or fittedness or something like that, and then leads to a certain amount of reproduction. But you see, I insist that that's a bogus causal model, because you see, how would you independently tweak this thing? Right. I mean, for that to be a genuine causal model, I mean, it's got to be possible to tweak this thing and to observe some change on the effect variable. But I say there's no such. I say if you fully specify the environment, then there's no, then immediately W will be a function of that and the genotype. I mean, well, obviously there'll be, you know, random factors, you know, as well, that will average out in a large population, but that's as always a model. So I mean, I think you're absolutely right that sort of circularity would result if we wanted the fitness concept to also explain why it is that some things have a high value of W and others don't. But I don't think that there's any reason to think that that really is one of the things that the fitness concept was meant to do. So you know, I'm glad you raised that question. Thank you.
Thank you. That was really cool. I learned a bunch of things. So my question is about this tautology reply. These tautology actions. So I take it you don't want to say it's a tautology. It is, right? And I was gonna, yeah, and I was gonna ask about that. And I think at some point in the talk you said it's not a tautology because it could be that like change is driven not by fitness but by like random change more or less. Well, and I was wondering whether any of these models that you talked about are sort of like capacious enough to sort of like model, like include both hypotheses. I mean, ideally we want a model that sort of like is big enough so that in the model, like we can sort of express the hypothesis that change is driven by fitness differentials and the hypothesis that is driven by like random mutations.
No, I mean, that's absolutely right.
Yeah.
So, I mean, I think that the statement that I say is not tautological, even if one defines fitness in terms of actual numbers of offspring, is the statement that fitness differences between types explain why it is that one type increased in frequency and another decreased. Because you see, another hypothesis is that there was recurrent mutation from one type to another. That could explain why one type is increased and another decreased. And indeed, sometimes that's true. Right. So therefore, it can't possibly be tautologically true that differences in actual amount of reproduction between this type and that type explain evolutionary change, because we found a different possible source of evolutionary change. So that's the response I'll make to the tautology objection in that form. Now, I mean, it's also true that in some contexts, that's not the right thing to say about fitness anyway, but for different reasons. If one is explicitly trying to model the phenomenon called demographic stochasticity, which means simply stochastic factors that affect an individual's reproduction independently of others of the same genotype. So that would average out if there were enough of them. In general, one will want to define the fitness of an individual by expectation, by the expectation. But the reason for doing that is not because you're trying to avoid a tautology that would result from taking fitness to be the actual number, because that's no such tautology would result. The reason for doing that is simply that you're trying to incorporate stochastic factors into your model. So in short, sometimes we do indeed want to define fitness in terms of actual reproduction, and that doesn't trivialize explanation of evolutionary change by means of fitness differences. Sometimes we don't want to do that, but the reason for doing that is not that we're concerned to avoid some threat of circularity, because there wasn't one anyway, but rather that we're trying to explicitly just model the stochasticity. Now, your second part of your question is a good one, which is to say, look, can we explicitly incorporate all of these different factors into complex evolution modeling? Indeed, yeah, I mean, that's exactly what a lot of evolutionary modeling will do, is to explicitly make assumptions about mutation from one type to another and about selection. The most, perhaps the most best known result in that discussion is an old formula known as the selection mutation balance, which shows how we can have an equilibrium in a population where frequency of a gene is the same, because the force of selection in favor of the gene and mutation away from it directly balance each other out. So that's an example of how one might model them together. I mean, when you want to put together natural selection and random factors, or so-called drift, into a single model, then it becomes a whole lot more complicated, conceptually and mathematically. But this has been there's been a huge amount to say about that. It's been a long focus of discussion for a long, long time. And absolutely is something that one wants to do.
I wanted to ask, say more about the sense in which when evolutionary biologists are arguing about the right fitness concept, there's no dispute about the science.
Yeah.
Because I find it puzzling.
Yeah.
And I was trying to think of an analogy with when philosophers argue about causation, they come up with recherche examples, and it seems like there's no disagreement among philosophers about all the true counterfactuals, whether there's energy transferred and other things. In some sense, all the substantive stuff they agree on, and they just disagree about whether to put this honorific, that A caused B. Is it like that, or is it when I looked at the end at your two types of disagreement, type 1 and type 2, they look a bit more substantial. They look not just like verbal disagreements, but maybe disagreements about what's the right thing to model.
Yeah, no good. Yeah. How it would compare to that analogy you have with this causality? I have to think that one through. That's an interesting analogy. But I do think they're non-trivial debates, but nonetheless the science is settled here. So perhaps one of the examples I'll come back to is this geometric mean business. Okay, so the model that we have here then is in effect that there are a number of different competing types in the population. So
we can try this one. Better? That looks a bit better.
So we've got the competing types in a population, and then we've got a set of environmental states. Let's call that set X. That's a set of environmental states, and say there are 2 or 3 possible states of the environment. And there's a probability distribution over these. In the simplest case, we assume that's independent across time. So there's no autocorrelation of the environment. And then for each of the types, then we can compute as a function of the state the per capita number of offspring that an organism of that type will leave. So we just make the large population assumption here. So that that can be assumed a fixed parameter. So for example, WAS1 says that 1.2 or something, that says that in environmental state S1, organism of type I will leave on average 1.2 descendants. Okay, and then we say, well, which of the 4 types then, A, B, and C, and D, has the advantage? Or is going to evolve? What's the least fittest? And then one way you can broach that question is to say, well, look at the geometric mean of this quantity here, WSIA, over those environmental states. Do that for each of the 4 types and see which has the highest value of that geometric mean. And some people say that measures which is fittest. But then the question is, well, what information does that tell you? Well, that tells you that with probability 1 in the long run, the type with the highest value of that will be the only one in the population. Its proportion of the population will tend towards 1 without limit as the number of generations goes to infinity. That's the reason for saying that that's the right measure of fitness here. So if we say, well, what are people implicitly saying fitness is meant to do? The answer is predict the outcome of evolution. But you see other people say, no, 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 no. They don't dispute that that's true, but they say that's not the right fitness measure. Because what we really are interested in, what we really want fitness to do, is to be able to tell us the new frequency as a function of the old. That this thing here, this quantity here, should be relative fitness. It's fitness divided by the mean population fitness. That really fitness is implicitly defined as whatever quantity allows us to work out the new frequency as a function of the old. Now in this case, of course, the new frequency is a random variable. So there's no possibility of saying what it is. But we might very naturally say, well, what's its expected? What's the expected frequency of the type over the next generation? Then we write that's simply the old frequency times the expectation of the relative fitness, which incidentally is the expectation of the ratio of two random variables. So one being the fitness of type A itself, and the other the average fitness of the population. And so some people say, look, that's the fitness of each type, not the geometric mean. And those things are not equivalent numerically, and they're not ordinarily equivalent either. So the model here is extremely simple. You can work out what will happen eventually. And so it really just depends on whether you think the fundamental job of the fitness concept is to play this long-run predictor role, or is to determine the expected evolutionary change over a generation or not. And at some level, that is semantic, I guess. Yeah. But it can see, I mean, that's what I mean when I say that the science is clear. You know, everyone agrees on the model is so simple here. It's simple. But nonetheless, there are two plausible candidates for what fitness might be taken to be. And as I see it, it all stems from, we start, as Darwin did, with the sort of simplest case in mind, where they coincide. And then we add in the complexity of a stochastically varying environment. And then we get this parting of ways. So how that maps onto your causation example, it's actually an interesting one. I mean, the way I like to express it, as I have done many times, is to say, look, the science is clear, but nonetheless, people can argue about what the right fitness measure is. How could that be? Well, here's why, if you like. But whether that's purely semantic, yeah, I guess it is, because I mean, strictly speaking, you see, I'm saying there are 4 different fitness roles, and that really means there are 4 different fitness concepts. And so, yeah, I mean, strictly speaking, I guess the philosophy of language thing to say is, yeah, the meaning of the term is different as the two people are using it. There is an equivocation going on. But I think sort of to explain why there is that equivocation and what it is, you need something like this story about roles.
Thank you.
Yeah, thanks. This is extremely interesting and helpful. I really do appreciate this role realizer distinction and separating out these different roles. I think it's an extremely valuable angle on this literature. I'm going to try to maybe press back on you know, what you've said about the way Mills and Beatty have positioned their original propensity interpretation, and then maybe you can tell me if I've misread them. I think that, you know, with this distinction between the reproductive outcome and the actual evolutionary change in Mills and Beatty, and in most of the fitness literature since, I think I've made this mistake as well while talking about Mills and Beatty, is to just implicitly assume that reproductive differences are the only thing driving the dynamics in whatever simple model you're discussing. And so these things like migration and mutation, all these other things, it's just implicitly assumed to be symmetrical or non-factors. And then it seems like there's a revenge of the tautology problem, because now we have the explanandum of actual evolutionary change is just going to be essentially the same thing as the explanandum of reproductive differences, because it's the only, X hypothesize the only thing making the difference. And now it seems like these probabilistic tendencies toward reproductive success of the sort that Mills and Beatty invoke are useful explanands.
Well, you see, I mean, you certainly could make model assumptions that there were no other possible sources of evolutionary change if you wanted. But then, of course, I mean, if you wanted, then the question would arise whether in any real population, your model assumptions are appropriate. So then, I mean, if you then explained, I mean, if you tried to explain what's going on in a real population where there has been an evolutionary change, I mean, the answer might be your model assumptions don't hold with that population. You see what I mean?
Yeah. So take like the Florida panther conservation effort in the 1990s. Tiny inbred population of mountain lions in Florida, and as far as I know, the explanation that conservation geneticists were concerned with was of why so many deleterious alleles and phenotypes were fixed in that population was just essentially drift, stochastic, because of the extremely small population.
Right.
And so in an instance like that, I would think, okay, well, it's not that there couldn't, I mean, there was mutation, and it's not that there couldn't have been migration or anything like that. It's just that the thing that we're actually trying to explain, we think, is due to stochastic fluctuations in reproductive differences. And in those kinds of instances, it seems like I'd want to use these probabilistic tendencies or
yeah, I mean, you see, I think there's nothing wrong with the idea that given an organism's genotype and given the environment, in a real population, there may well be a number of its survival, say, to reproductive age, is not fixed. I mean, it's a probabilistic matter. You could just get eaten by something, or something, suffer from some misfortune. So there's absolutely nothing wrong with that idea in itself. And indeed, in some cases, we model that explicitly in a model that is incorporating demographic stochasticity, which is basically the demographic thing that's given rise to drift. So, I mean, it's not that I think it's wrong to say that there are these things, these propensities, if you like, to leave different numbers of offspring or to strive to in an environment with greater or less chance that organisms have because of their genotype, and where they may differ systematically depending on the genotype. I don't think any of that is wrong, but I still maintain that, you see, most of the time when people are talking about expected number of offspring, they're not in fact taking the expectation of such a probability distribution at all, right? Really just what they mean is there's lots and lots of individuals out there. You pick one at random, measure its phenotype, or measure its number of offspring, and then take the expected value of that random variable. So the random, I mean, you see, Beatty and Mills and Beatty don't make clear if they're trying to describe fitness as it's used in a finite population model or an infinite population model. And in both cases, you'll find a quantity called the expected number of offspring of an individual. But they have a different meaning in the two cases. In the finite population case, you're explicitly introducing a probability distribution over the number of possible offspring and taking its expected value. In the infinite population, very large population case, your only reason is for your reason, the reason for defining a random experiment by the random selection of an individual from that genotype, and then taking the expected number of offspring with respect to that probability distribution, is that to capture the fact that individuals with the same genotype will typically differ in fitness in their number of offspring. But that may be because of chance, but it may be also because we mean genotype at a single locus, and they'll differ genetically in all sorts of other, phenotypically in all sorts of other ways too. And so it need not be that there's actually any stochastic stuff going on, either in the model or in the world as being modeled. And it would still make sense to talk about expected number of offspring. So in short, it's not that I think Mills and Beattie say is sort of wrong entirely. It's more that I think they haven't distinguished the finite and infinite population case. They've moved from the correct observation that if fitness is defined one way, then differences in fitness couldn't explain X, to the very, very different claim that if fitness is defined that same way, differences in fitness couldn't explain Y. And have implicitly assumed, and this ties in with the first question we had, that part of the job of the fitness concept is to explain why it is that some types of organism lead more offspring than others. Whereas I say that's not part of the job of the fitness concept. I mean, we do want to explain that, but that's the explanation of that involves ecological stuff about why phenotype tended to help you survive more in this environment than that. But I still don't think it's entirely wrong to say that as a function of its genotype, given its environment, the number of offspring an organism will leave will partly be due to chance. And so therefore we can consider the probability distribution of the possible numbers of offspring of that particular individual if we want, and take the expectation. But I do think it's important to say that when people talk about expected number of offspring in biological models, that's usually not what they mean. So yeah, I don't know if that helps.
Yeah.
There's a lot to say about it.
So I wanted to ask you about whether this kind of definition of fitness can be helpful in understanding fitness outside of the organismic biology. So I think cultural evolution.
Good. Yeah. No, that's a nice. In fact, actually, that's just the section of this book that my co-author and I are trying to write at the moment. Because you see, in cultural evolution, there has been this big debate about what cultural fitness is meant to mean. So cultural evolution, people will know what that refers to. Actual spread of cultural variance or competing cultural variance across human populations, usually spreading horizontally down to offspring. And you see, some people have wanted to say something like, look, the relevant notion of fitness here is just rate of increase or something. And so if we go back to Fisher, right, then, I mean, the reason that Fisher's Malthusian growth rate, using parameter definition of fitness there, is not really yeah, I mean, the sort of objection to saying that that's a good measure of genotype fitness. I mean, firstly, it's not really clear that's what Fisher meant. But if he did, as many people took him there, if you take him literally, that's what he seems to say. That after all is the definition of exponential growth model. So if that really is what he meant, then the objection is, well, wait a minute. There are two completely different reasons why a type might have a higher value of that quantity than another. One is they're better at surviving and reproducing, and the other is they're produced more often by recombination from other things, because the type doesn't breed true in sexual population. You see, in an asexual population, that would be fine. So it seems that this putative measure of fitness is affected by two completely different biological processes. One is survival and reproduction, how good you are at that. And the other is how often the rate at which organisms with other genotypes produce offspring of your genotype. And they're completely different processes, and intuitively we only want fitness to reflect the first one. We see in the cultural evolution case, it's unclear whether that distinction really makes any sense. Some people have suggested it does, and indeed there are certain cultural evolution models that work like this. An individual leaves a certain number of sort of cultural offspring, and those are other individuals in the population who copy it, or try and copy it, but they may not succeed in copying its trait. So, but other people have said, well, wait a minute, that's a bizarre you're just artificially trying to model it on biology. But you see, in biology, we can make a very clear distinction between how many offspring an organism has and whether those offspring inherit some trait or gene from the parent. But can you make that distinction in the cultural case? Well, I think it's a bit unclear, really. I mean, think of what examples of cultural evolution, like a pop song diffusing around the globe because people can't get it out. It's on the radio the whole time, or something. And is it really the case that someone whistling that or having that pop song influences a number of other people, and then we can sensibly say, okay, this is the number of cultural offspring that individual left, and this is the fraction of them that inherit the whistle the same tune, and the other ones somehow didn't. They were bad at whistling, or they misheard whistle something else. It doesn't seem really that that's a plausible model always of cultural transmission. So for that very reason, I think, some people have essentially thought that this is the right fitness measure in cultural evolution, whereas other people have wanted to say, no, 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 that runs together reproduction and inheritance, as it clearly does, and problematically so in the biological case. So I do think actually that this particular part of my discussion does illuminate what's going on part of what's going on in some of these debates about cultural fitness. I mean, and put slightly differently, should you think of cultural fitness as attaching to a cultural variant or to an individual who has the cultural variant? I say probably the former, because it seems to me that this model that individuals leave cultural offspring, and then it's an open question whether those offspring in fact are characterized by the same cultural trait or not. It's to me a bit weird, really. I think just trying to model stuff on the basis of biology is really the only rationale why anyone thought about it.
Kelly.
Thanks. So I wanted to go to your response to
right,
because I was thinking kind of the exact same things. Feel free to just kind of convert what you presented for a moment. So my thought was when you got to the roles and walked us through these examples of how those roles are exemplified. Like, oh yeah, okay. So if you think the operationalization going on this model just is, then what you're presenting us is actually an explanation of how you get many concepts emerging. And not an explanation of wisdom. Where teachers have operationalization fitness, but I don't think that's what you're trying to do because you built this notion of freedom. So I guess I'm a little bit puzzled about what the notion of freedom concept is for you, the sense of like you would expect that when it comes to operationalizing something that the operationalization is not going to contain it's something like a definition of concept. So do you mean to talk about the concept of fitness as a theoretical concept, meaning concept, such that its operationalization is influencing.
Well, I didn't say the word operationalization. You see, and I'm a bit reluctant to. But so let me see if I understand what you're saying. It sounds important, actually. So I want to say, set this sort of semantic picture from Lewis, Carnap, and Ramsey, according to which the meaning of a theoretical concept is determined by its role in the theory. And so we say the definition of fitness then is the thing that does such and such a job. However, it turns out there are actually 4 different jobs. And so really the right thing to say is there are 4 fitness concepts, separate fitness concepts. And I think that, if true, implies that the word is polysemic. But of course, someone might say, well, look, here's a reason of some sort for prioritizing one of the concepts, sort of one of the roles over the other. So I can imagine someone saying, yeah, look, it's number 1, that's the real one. Some biologists have said number 2 is the real one. Others say number 3 is the real one. So, but I mean, if there was a way of sort of breaking the symmetry and saying that's the real one, then there would only be one fitness concept. So strictly speaking, I guess I am saying there are 4 fitness concepts, and the word fitness can pick out any of those 4 concepts. I want to say then that the definition of fitness, of any one of those fitness concepts, is fitness is the quantity that plays such and such a role, such that the type with the highest value of it dominates the population in the long run. For example, in the case of my role to predicting. So that's the form that the definition takes. And then I want to say a statement to the effect, a statement such as the fitness of a type is its geometric mean reproductive success over a stochastic environment, for example, is not a definition of fitness, but is a statement to the effect that a certain quantity under certain model assumptions realizes one of those roles. Now, my difference from the Lewis Carnap Ramsey story is that, you see, in the Lewis version of the story, at least, the thing that realizes a theoretical role is meant to be an object in the world. It's meant to be some worldly thing. Whereas as I've set it up, because of the model first way of looking at it, the thing that realizes one of the roles is a theoretical quantity in a model. See what I mean? It's a model-bound quantity, not an actual thing out there in the real world. So, but other than that, which admittedly is a big difference, because I'm employing the model-centric view of what a theory is. That's why it rises. But I think other than that, my position is semantically just the standard Lewis sort of functional role story. And so I think that you say I haven't really explained why it's polysemic. I mean, you see, I think in your question you talked about an operationalization of fitness, but I think that corresponds to what I described as the quantity that realizes a fitness role under certain model assumptions. But I wouldn't really call that an operationalization, because it still might be, in practical terms, impossible to empirically tell what that quantity is. Right. And so it would sort of fail what one normally thinks of as a test for something to be operational, and you can go into the field and kind of figure out what its value is. So for that reason, I hesitate to use the term operationalization. I prefer the term realization. But does that answer your question? I mean, so when you so you say I haven't really explained why the term is polysemic.
So I mean, it was helpful to clarify the difference between operational
I think we need to stop here anyway. Sorry for those who didn't have time to ask that question. We have a reception now on the 11th floor, so you can actually get hold of Samir and ask your question. I apologize for that. It's already time to 5:30, time to stop. So thank you, Samir, for this. Please join us to the Center of Philosophy of Science on the 11th floor for the reception.